Okay, so here's a picture you've seen in several lectures to this point. You're looking at a panoramic photo that I took on a trip to Salt Lake City probably a decade ago. It was my family on that trip, really happy to stand next to one of the big tires on the haul truck. Super impressed. And all I want to emphasize is we've got a large hole in the ground. Last lecture we talked about how that hole in the ground evolves. So how mining geologists and mining engineers, they detonate rock, they pick it up with shovels, they put it into trucks, and then it leaves the mine. And as a function of time, since this mine began in 1906, the hole has gotten deeper, and as it gets deeper, it gets wider, and that's for slope stability around the edges of the open pit. And since 1906, Bingham Canyon has produced 22 million tons of copper, which as of right now would satisfy global demand for about 18 months. And they've also produced a significant amount of gold and silver and molybdenum. You don't need to know these numbers for gold, silver, or molybdenum. I've shown you that we have empty haul trucks that go down to the bottom. They're filled up with several hundred tons of ore grade rock that comes back up to the surface. And what I want to talk about today is what happens to that ore grade rock when it comes back to the surface. The photograph on the left side of your screen is of ore grade rock from Bingham Canyon. And I'm going to introduce a term here, gangue minerals, Gangue. And all I need you to know about gangue minerals is that they are economically worthless. So when we look at this rock, the thing that I want your eye to be drawn to are all of these dark or opaque, blackish colored minerals that are speckled throughout the rock. All of those dark opaque minerals, those are ore minerals. And in this case at Bingham Canyon, they are dominantly the mineral chalcopyrite. Chalcopyrite is a mineral that contains copper and iron and sulfur in this stoichiometric ratio. And chalcopyrite is about 1/3 by weight or mass copper. So about 33% of the mass of chalcopyrite is copper. Now, in this particular ore deposit, the grade of ore is about 1 weight% copper. So if copper is 1/3 of the mass of chalcopyrite and the grade of ore is 1 weight% copper, then chalcopyrite constitutes about 3% of the ore grade rock, which means that about 97% of the ore grade rock is gangue minerals. And you can think of those again as waste minerals that cannot be sold because they do not contain any metal that can be sold on the open market. Here are two images just to emphasize the ratio of the ore grade sulfide minerals to the gangue minerals. They're of the same rock from Bingham Canyon. The image on the left is a transmitted light image. So imagine that you could slice the ore grade rock to about the thickness of paper and put it on a conventional microscope and shine light up from the bottom or the back of your screen. The light would go through the sample and then you could see that through the microscope objective. Transmitted light does not go through sulfides such as chalcopyrite. So these copper iron sulfides labeled here that show up as black, those are the minerals the mining company wants. The image on the right is what we call a backscattered electron image produced from a different type of microscope. And you don't have to know the details. You can talk to me during office hours if you're curious. But again, here, the sulfides show up as white or very bright because they have a very high atomic density relative to all of the silicates. So all of this bright here would be sulfide, and then what's labeled potassium feldspar would be this lighter gray color here, and then you can see it over here. And much of this sample is actually composed of the mineral quartz. So what mining companies have to do at this stage, they bring the ore grade rock out of the open pit. It's in the back of a truck. What they have to do now is they have to physically separate these sulfides from the gangue minerals. How do they do that? Imagine you're at Bingham Canyon and you see a haul truck coming out of the open pit and it's filled with several 100 million tons of ore grade rock. And that ore grade rock is 3% chalcopyrite, 97% gangue minerals. How do you physically separate the chalcopyrite from the gangue minerals? That's what I'm going to focus on in the first part of the lecture today. And it falls under this umbrella term, beneficiation. So the mining company ultimately benefits by separating chalcopyrite from the rest of the rock, all of the gangue minerals, and then purifying that copper, as we'll talk about in the second part of the lecture today, so that they can sell that pure copper metal to companies and investors around the world. There are two types of beneficiation. The first is physical beneficiation. The second is chemical beneficiation, and we're going to walk through these in order today. The first part, physical beneficiation, involves what's called a ball mill, where the ore grade rock is ground to about the consistency of bread flour. So if you've ever made flour, just imagine holding that flour in your hand and moving it around on your fingertips. You know how incredibly small it is. So a ball mill, a photograph on the left shows you one of a ball mill actually at the Bingham Canyon mine near Salt Lake City. And what I want you to look at is the GIF on the top right. And for now, just see that the ball mill is rotating. Okay? It's rotating counterclockwise, as I'm showing you here with the laser pointer. And inside the ball mill, we've got steel balls, which are shown in black. So think of those as steel balls like billiard balls or bowling balls, very, very strong. And those balls are being rotated up the side of the ball mill, and then they fall back down. And as they do so, they're crushing all of the ore grade rock, which is shown here as the black and white stippled specks. There's a lot of engineering that goes into grinding. So I want to show you a video that walks through some of these details just to give you a sense of, among the most important things is, what is the size of the ore grade rock that is put into the ball mill? What is the size of the actual balls themselves? And then what is the rotational speed of the ball mill? So in this video, they're using steel balls that have diameters of 10 millimeters or 3/8 of an inch. It's a scaled down ball mill, so you can just get a sense of what it would look like if you scaled this up to the size that we see at operating mines. And they're going to talk about speeds and the role that speeds play, meaning the rotation of the ball mill. So a subcritical speed has a rotational velocity of 85 revolutions per minute, right? So think about your washing machine at home when it's on the spin cycle and it's spinning very, very, very fast to push the water out of your clothes and get that out of the washing machine. We're going to look now at a ball mill, and initially there's going to be no ore grade rock in the ball mill. And I'm going to let this play through, just stopping it periodically. So here we have our ball mill. Okay, this is what we're looking into here. This is open space. This on the outside is the steel that comprises the ball mill. And this circular part of the ball mill is what's going to rotate. And we've got balls inside. And again, these are steel balls, 10 millimeters or 3/8 of an inch diameter. And notice what happens at a speed of 85 revolutions per minute, right? You can see it's spinning, and it's spinning counterclockwise. And notice that the balls move up the side of the ball mill, and then they fall back down. So no balls make it all the way up to the top at this particular speed. Now notice what happens when they slow it down, okay? But they're at a subcritical speed. And so now they've reduced the frames per minute, and you can see what's happening. The balls are moving up along the inside of the ball mill and then falling back down. So they're grinding on each other, okay? Something referred to as nipping. Move past this a little faster, right? So here you can see on the top where they're just falling back in on each other. Okay? This is what we think of as good grinding action. Okay? And that'll become apparent as to why. Oh, we'll get back to where we were. This will become apparent when you look at what happens to the action of the grinding process when the speed is changed. So now we're putting feed in. So let me back up a second here. So by feed, what is actually being put into the ball mill now, this feed is ore grade rock. And the ore grade rock has a size of about 1 to 2 millimeters per grain. And they're filling it at about 25% of the amount they would normally fill. So now you can see in the video that the balls within the ball mill, they're smashing into each other and they're smashing into the feed. Okay, so they're grinding up this ore grade rock. The ore grade rock starts with a diameter of 1 to 2 millimeters, and as it's being pulverized by the balls, the grain size or the diameter of the ore grade rock decreases the longer it's in the ball mill. Now they're going to increase the speed of the ball mill, and let's watch what happens. When you increase the speed of the ball mill, it can become too fast, meaning that above a certain speed, above a certain revolutions per minute, the speed is too fast and the grinding is actually inefficient. So the goal here, and I'll come back and touch on this towards the end of the lecture, the goal here is to optimize the speed or revolutions per minute, which takes energy, right? So there's electricity that's being used to spin the ball mill, and the more energy you need, the more it costs the mining company. And if spinning it too fast requires more energy, and it's inefficient and doesn't produce a final grain size that you want for the next step of the process in beneficiation, then that is something the mining company wants to avoid. So the goal here again is to optimize the right size of the ball, the right speed revolutions per minute, starting out with the right diameter of ore grade rock. And then when that ore grade rock is put into the ball mill, they want it to be ground so that all of the grains that come out after rotating in the ball mill are a uniform, consistent size. So that's the end goal here, is they want that uniform, consistent size of the balls, of the excuse me, not of the balls, of the grains. So when they increase the speed to 100% critical speed, whatever that may be, notice what happens here. Right? Now it's just rotating around like a big slurry. So this is inefficient. It's also a waste of money. It's spinning too fast, which requires lots of energy, and the grinding is inefficient so that you end up with a range of different grain sizes, which is not what the mining company wants. So if we go back here to our subcritical speed, notice here that the balls essentially always stay in roughly the lower part of the ball mill, and the end product here will be ore grade rock that has been pulverized from approximately 1 to 2 millimeter diameter into a flour grain size ore grade rock. So here again is what we started with. Here was our ore grade rock. And now after the ball mill, look what's happened. Now we have the flour consistency ore grade rock. It's been pulverized. The scale bar down here is 0.01 inches. So very, very, very fine grained. We have all of our gangue minerals that we started with. So we still have 97% gangue minerals. We've got 3% ore mineral grains. And here the ore minerals are chalcopyrite. And then the black here, as I indicate, that flour consistency ore grade material now, we've set that in an epoxy resin or plastic to mount that to look at on a microscope. So now what do we have? Now we've gone from ore grade rock that was rock, we crushed that up, and now we have flour ore rock. And now the next step is to figure out how we actually separate these very fine grains of chalcopyrite and other sulfides from the rest of the rock. So we've still got 3% chalcopyrite, we've still got 97% gangue minerals. Now we have to figure out how we separate those two from one another, so we can end up with a pure chalcopyrite separate at the end of physical beneficiation. So how do you do that? What's the next step? How do you separate the 3% chalcopyrite from 97% gangue minerals? What would you do? So I'm going to review some facts about the minerals chalcopyrite and quartz, where I'm using quartz as a proxy for all of the gangue minerals, all of that 97% of the rock. So chalcopyrite, which is copper, iron, and sulfur, has a density of about 4.19 grams per cubic centimeter. Quartz, which is silicon and oxygen, has a density of 2.65 grams per cubic centimeter. And the photograph I show you here on the right side of your screen are footsteps along the beach. This is the ocean on the left side, and the waves are lapping up on the beach. The quartz here is the same quartz that you would walk on if you were at the beach. So quartz has a lower density than chalcopyrite. Now I'm going to introduce water. So we've got a beaker here filled with water, and water is hydrogen and oxygen, H2O, and water has a density of about 1 gram per cubic centimeter. It's technically a little lower, but let's just go with 1 and be happy. So what do you predict will happen if you drop chalcopyrite and quartz in the beaker of water? You'd end up with the same scenario that we talked about with those magmatic sulfide mineral deposits. In this case, chalcopyrite and quartz will sink because they're denser than water. So chalcopyrite with a density of about 4.2 grams per cubic centimeter, quartz with a density of 2.65 grams per cubic centimeter, they will sink through the water that has a lower density of 1 gram per cubic centimeter. So you can't imagine a process where you could just drop chalcopyrite and quartz in water and separate chalcopyrite from quartz and all the other gangue minerals. There has to be something else that we can do. In the 1880s, Carrie Everson, a photograph shown here on the left side, she was able to come up with a process for which she was awarded 2 United States patents that revolutionized economic geology, or the science of extracting ore-grade rock and processing it so that you can purify the sulfide minerals such as chalcopyrite from the gangue minerals. And her observations were truly like rocket science at the time. What Carrie observed is that when she took chalcopyrite and other sulfide minerals, and she took gangue minerals such as quartz, and she observed their behavior in the presence of oils. So think corn oil, soybean oil, canola oil, which are fats, right? So these are lipids. She observed that the fats stick to the sulfides, but they do not stick to quartz or other gangue minerals. And you might think, well, that sounds relatively simple. And today it is. But if we go back to the 1880s, her observations, which led to 2 patents, put Bingham Canyon on the map as the first ore deposit to be mined using a process I'm going to describe today. So what Carrie figured out was that if you take chalcopyrite and add it to oil or fat, the oil fat sticks to chalcopyrite. It's what we call it wets the chalcopyrite. Whereas if you take a mineral like quartz and you add it to fat or oil, the fat does not like to stick to quartz. Okay? So quartz does not like fat, chalcopyrite and other sulfides do. Now, what Carrie then did, getting to her revolutionary advances in economic geology, is she added sulfides like chalcopyrite plus quartz plus fat or oil and put them in water. And she noticed that fats will rise to the top of the water column, something we'll observe, and I'll show you a video of this in a minute, because fats or oils have lower density than water. Chalcopyrite and quartz would still sink through the water column, but on the individual grains of chalcopyrite at the bottom of the water column, they would be coated with fat or oil, whereas quartz would have no fat or oil on it. This is because chalcopyrite and other sulfide minerals are hydrophobic, whereas quartz and other gangue minerals are hydrophilic. Now, hydrophobic means water-hating, and hydrophilic means water-loving. So if you look at the schematic here, a hydrophilic mineral, such as quartz, when water comes in contact with the surface, that water will spread out along, in this case, a mineral such as quartz, okay? versus a mineral such as chalcopyrite on the right-hand side is very hydrophobic. So notice that the water beads up and it doesn't spread out on the surface of a mineral such as chalcopyrite. So chalcopyrite and quartz have very different behaviors when in the presence of water. Water will not stick to chalcopyrite, but chalcopyrite will stick to oil, whereas water will stick to quartz and oil will not. So the next breakthrough was taking advantage of the fact that fats or oils are hydrophobic, which means that it also does not mix with water. So this is why when we mix fat or oils with water, they remain immiscible. They do not mix. Now we know this, and I'm going to show you a video of something you already know, but just to make sure everybody's on the same page with respect to this concept of immiscible water and oil.
For this experiment, you are going to need a clear bottle with a lid. So I'm using a mason jar. And the first thing I'm going to do is I'm going to fill my jar about halfway full of water. Then I'm going to take a couple drops of food coloring and add it to the water. And you can use any color you would like. I'm going to stir that up. So now I have my water in my jar. And the next thing I'm going to do is add some oil. So I'm going to fill the jar with oil till it gets to about 3/4 of the way full. Then I am going to place the lid on the jar, and I'm going to make sure that it is really tight. Okay? And then once I have the lid on very tightly, I'm going to shake it to mix the oil with the water. Okay? I'm going to shake it about 30 seconds, and then I'm going to set it down and watch.
So what happened? Right? The video starts by adding pure water to the jar, some food coloring to turn the water dark green, oil is added, and then the jar is shaken, and you'd think, well, why wouldn't the oil and water mix? The reason they don't mix is because they are immiscible, meaning that they are two fluids thermodynamically that will not mix with one another. So despite the vigorous shaking for 30 seconds, notice what happens. At the end of the video, we end up with a layer of water at the bottom, and we end up with a layer of oil at the top. And again, these were revolutionary observations in the 1880s. So here's just another slide to emphasize what's happening there. We've got fat or oil with a density of about 0.9 grams per cubic centimeter, and we've got water with a density of about 1. So water is slightly more dense than the fats or oil. And if we pour fat or oil into a beaker or a jar of water and we mix it, we will never get the oil to mix with the water. After we set the jar down, we will end up with separation, oil at the top and water at the bottom. So what's next? Now I'm going to add one more ingredient, and this was the process in the 1990s that led to Bingham Canyon becoming the first type of its mine around the world that a company could extract the ore grade rock and process it to physically separate chalcopyrite. So now we've got chalcopyrite, density of 4.1, quartz, density of 2.6, fat or oil, density of 0.9, water with a density of 1, and air has a density of 0.001. So air is much less dense than the water, the fat or oil, the quartz, and the chalcopyrite. We know that chalcopyrite is hydrophobic, so it doesn't like water. We know that chalcopyrite likes to stick with the fats or the oil. And we also, because of work done in the 1890s, we know that fats or oils, they like to stick to air. So air is also immiscible with water. So if you imagine that happening in a glass or a beaker of water where we have an air bubble, the oil, as I indicate here and trace out with my laser pointer in black, the oil will coat the outside of the air bubble. And then chalcopyrite, here shown in yellow, will stick to the oil, right? So we've got a three-phase system. We've got a bubble of air, it's being coated by oil, and sticking to that oil is chalcopyrite. Now, mining companies today use pine oil as the oil of choice because it's benign and it has no negative environmental impacts if it were to somehow be released during the mining process. So imagine we've got an air bubble in a beaker of water. If there's oil in the water, the oil coats the air bubble and the chalcopyrite will stick to the oil coating. And remember, we've just ground this chalcopyrite so that it has about the grain size of bread flour. So it's incredibly fine grained. In the same beaker of water, that air bubble coated with oil will not stick to quartz. So quartz and other gangue minerals will not stick to pine oil or any other fat or oil. So this is really different than for chalcopyrite that sticks to the oil, which itself coats the air bubble, whereas quartz and other gangue minerals will not stick to oil that is coating an air bubble. So imagine this system where we've got our beaker of water, we've now got our flour-sized quartz and other gangue minerals and chalcopyrite. We've got air, which is much less dense than water, fat, which is also less dense than water. So air and fat, both on their own, they want to buoyantly ascend through the water to the top. And chalcopyrite sticks to the fat or oil. So the discovery in the 1880s and 1890s was that you could set up a system like this so that you could actually float the chalcopyrite to the top of the water column, even though it's more dense than the water itself. I'm going to walk through now in a few slides and show you this in still form, and then I'll show you a video of how it happens. So you're looking here at a schematic of what's called a froth flotation cell. The cell is simply this. So the cell is a cylinder coming into and out of your screen. It's got walls on all four sides, and it's got a floor, but it's open at the top. Now there are four inlets or outlets connected to the cell. There's an inlet on the left labeled 1 with the arrow showing you that something's going to flow into the cell. There's an inlet up at the top labeled number 2, and that is where air is going to be blown into the cell, and it comes in via this pipe that extends all the way to the bottom of the cell. And then there are two outlets over here labeled 3 and 4, and I'll show you what comes out of those. So again, we're putting air into the cell, we're putting something via number 1 into the cell, and then 3 and 4 is where we're allowing two different things to leave the cell. Now, this is an actual video of a flotation cell, and I just want to highlight everything here that I'm tracing out with the laser pointer is water. So we're looking now at the inside of a cell which is filled with water, and this part here is this. So air is going to come in through here, and I want you, before I hit play, to see right here. So the outside of this inlet is going to remain fixed. So it's bolted to the bottom down here. Hard to see, but just believe me that there are bolts holding it to the base of the flotation cell. And then this is essentially, you can think of it as a wheel that's going to spin. So air is going to be injected from the top, and then as that air is injected and forced to the very bottom of the flotation cell, which is open at the top but closed on all the sides and the bottom, this is going to spin much like a paddle, and I want you to watch what happens.
In mechanical flotation cells, the air is introduced into the blades of a rotating impeller. The air accumulates behind the blade and is therefore traveling at a high speed relative to the slurry. The relative motion of air and slurry causes shear at the boundary, and the air is broken up into tiny bubbles. The speed of the impeller will affect the size of the bubbles produced.
So if I go back to the beginning, right, there's no motion here, but as the video plays through, let me turn its sound off. As the video plays through, you can see the propeller now is spinning at a high rate of speed, and air is now going to be forced into this inlet. And as the air is forced into the inlet, it's coming in as an air stream. So imagine just taking a big deep breath out. You've got a big parcel of air coming out of your lungs. And think of it as one large amount of air or single volume of air. But what this propeller does at the bottom of the inlet here is it breaks up that air into an infinite number of small bubbles. So notice how now it becomes extremely cloudy. Each of these are small bubbles. Okay, if I back it up and we start looking now at the air coming out, that propeller is breaking up that airstream into an infinite number of bubbles. Those bubbles have densities that are orders of magnitude lower than the water within the flotation cell. So those bubbles are instantaneously going to ascend up to the top of the flotation cell because gravity takes them up because they are more buoyant, less dense than the water. So in this case, all we've done is we've injected air into the bottom of the flotation cell and we've broken it up into an infinite number of bubbles. So the next thing we're going to do, shown on the left side of the screen over here, is now we're going to inject what is called pulp. And pulp is our flour ore grade rock. So this is what we produced from the ball mill. And that ore grade rock flour has been added to water plus oil, and the oil here is pine oil. So we've got pine oil, water, and ore grade rock. And remember that within the ore grade rock or flour, chalcopyrite wants to stick to the oil, and the gangue minerals, they are hydrophilic, so they will not stick to the oil. They would rather be coated by the water, which allows us to separate chalcopyrite from the gangue minerals, as we'll see. So we've got air coming in, we've got a propeller at the bottom, it's generating an infinite number of bubbles. Those bubbles are ascending buoyantly to the top of the flotation cell, and now we're injecting this pulp into the flotation cell. And when that happens, chalcopyrite will stick to oil, and oil will stick to the bubbles, and those bubbles coated with oil sticking to chalcopyrite rise to the top of the flotation cell, and they form what we call a froth at the top of the flotation cell. And that froth, we literally scoop it out at the top via this outlet number 3, and that is what we produce a chalcopyrite concentrate from. And I'll show you a video and a photograph of what I mean by chalcopyrite concentrate. Whereas all of the gangue minerals, okay, which were part of the pulp initially, all of those gangue minerals, okay, because we're agitating the system here, all of those gangue minerals, which do not stick to oil and do not rise with the bubbles, those are pushed out via this outlet number 4. So what have we done? We've now separated chalcopyrite, 3% of the rock, from all of the gangue minerals, which are 97% of the rock. And I mentioned here that that pulp is now pumped to a tailings pond. We'll come back and talk about that in a subsequent lecture. So I'm going to play now an animation of how this process happens. So pay attention because there are going to be 2 particles that each have a different color, and the video will explain what each of the colored particles are, and I want you to watch what happens.
Air bubbles introduced into an agitated pulp collide with particles. Here, the hydrophobic particles are shown in brown, and the hydrophilic particles are shown in yellow. When the particles hit the top of the bubble, they begin to slide around it. While sliding towards the bottom of the bubble, the hydrophobic particles will become attached. At the bottom, the hydrophilic...
So let me just restate that. The hydrophobic particles, chalcopyrite and sulfides, attach here to the oil that coats the bubble, and hydrophilic particles, all of those gangue minerals, sink to the bottom.
At the bottom, the hydrophilic particles will fall away. Also at this point, some of the less firmly attached hydrophobic particles may detach and fall away.
So I'll play this
While
through
of the
again
bubble are
just so
shown
you can
and
see
the
what's happening,
hydrophobic
right? We've got two different types of minerals that they refer to as particles. And watch what happens here.
particles. Here, the hydrophobic particles are shown in brown, and the hydrophilic particles are shown in yellow. When the particles hit the top of the bubble, they begin to slide around it. While sliding towards the bottom of the bubble, the hydrophobic particles will become attached. At the bottom, the hydrophilic particles will fall away. Also at this point, some of the less firmly attached hydrophobic particles may detach and fall away. Hydrophobic particles may detach. So at this point,
So here we've got a bubble that is literally attached to sulfides because it's coated with oil, and oil likes the sulfides, or vice versa, the sulfides like the oil. And now that bubble is going to float those sulfides to the top of the flotation cell, which allows the mining companies to separate the chalcopyrite from the gangue minerals. Okay?
the froth in the first few cells of a bank is often heavily loaded with hydrophobic particles. The froth appears dense and heavy. The bubble size is small due to the stability imparted by the particles. As you move down the bank, the appearance of the froth will change. There are not as many hydrophobic particles available to float, and thus the froth loading is lower. Windows appear and froth stability decreases, resulting in larger bubbles, many of which will burst.
So this is what you would see at the top of the flotation cell. So here you're looking at bubbles that have risen to the surface of the flotation cell, and the color is literally the color of the chalcopyrite sulfide minerals. And notice here on the sides that all of those bubbles and the chalcopyrite that coats the oil on the bubbles is being scooped off the side into a trough. And when it's scooped off the side into a trough, it can be collected. And at this particular froth flotation facility, there are dozens of flotation cells lined up one after another. And this is a process that goes on 24/7, 365. It never stops. So this is a video just to give you a sense of what a flotation cell looks like at a particular mill. So each of these large cylinders here is a flotation cell, and now you're looking top down. So all of these bubbles were injected. Those bubbles get coated with oil. The oil sticks to chalcopyrite, which comes to the surface, and here those bubbles overflow, and that in this particular facility allows them to separate sulfides that contain copper and nickel. So those observations made back in the 1880s allowed mining companies to start mining rock that has only a few percent chalcopyrite or other sulfides. Prior to these observations and the patents that were earned in the 1880s and 1890s, ore grade rock such as Bingham Canyon was not ore grade rock because there could be no process that was profitable used to separate chalcopyrite from the rest of the gangue minerals in the rock. This is also something that mining companies work on. So there is an entire field of metallurgy, mostly in engineering programs around the world, where engineers will try and perfect this process. Things such as the pH of the water, the exact constituency of pine oil, its composition can affect froth flotation. So mining companies will do lots of small-scale tests to try and improve efficiency and recovery, because remember, their ability to make money depends on the amount of chalcopyrite that they get out at the end of this process. So they want to extract 100% of the chalcopyrite and other sulfides. If they only extract 90%, 80%, 70%, it's less revenue, which means less profit. So what next? So the next step is we have to take all of this ore grade chalcopyrite now. Now we have a concentrate. The concentrate is almost pure chalcopyrite. It has a particle size equal to about bread flour, very tiny particles of chalcopyrite. And it looks like this on the right. So this is actually a mountain of flour-grade chalcopyrite with humans for scale. This is a photograph I took at a facility in Arizona in 2006. And this is almost 100% chalcopyrite. And from here, it gets put in bags. And we'll walk through and talk about the next step of what a mining company does now that they have this chalcopyrite concentrate. But before we do that, back to energy and economics, I want to let you know that mining companies are also trying to come up with different technologies to pulverize the rock. So different technologies that would allow them to reduce the amount of energy required, because energy is money. So I'll play this through just to let you see another relatively cutting-edge technology that mining companies have started to turn to, because it's less expensive than operating the ball mills.
This is an experimental 500 kilovolt marked generator feeding its output into a rock disaggregation chamber. A 50 kilovolt pole transformer charges the 5 pulse capacitors through the large inductors. The water and electrodes become the 6th capacitor, creating an incredible release of energy into the rock core samples. The explosion containment vessel is made from 2-foot square, 1-inch thick sheets of nylon, and it was the only material found to handle the intense blast. The purpose of the rock disaggregator is to separate mineral samples at the boundaries without fracturing the grains. Mechanical crushing systems usually fracture small grains or gems, but this system separates them without damage. The charging output is set on low for 5-second pulses. After 10 or more discharges, the rock core sample is completely broken down. The different minerals are separated without damage, allowing a more accurate examination. Larger bits of rock can now be removed using a sifting screen, leaving only the important minerals.
So this is just a different technology where the ore grade rock is put into a solution that conducts electricity. And notice the ore grain rock goes in and it's very coarse grained. So these are drill core. And then electricity is pulsed systematically through the fluid, and that disaggregates the rock. And it turns out that this technology has the potential to be less expensive than the ball mills. And notice here, as the video plays through, and the person pulls out some of the disaggregated rock, now you're looking at these sulfides. Now, they're certainly not flour consistency yet, but companies are working on adapting this technology so they can scale it up back to economy of scale so that it will allow mining companies to reduce their costs. And just a few words here, this technique, electrical pulse fragmentation, uses about 20% less energy than other techniques. Less energy means lower costs to pulverize the rock, and lower costs means higher profit, which is something that mining companies are always seeking. How can they increase their profit margin by reducing the costs of all parts of the production process? So the technique goes from ore grade rock at the left to fine grained rock at the right, and it would need to be even further ground in order to do what I'll talk about later in the lecture. There's lots about this written in the literature, and so I'd encourage people, I just grab screenshots of a couple articles here. I'd encourage people to look through this on your own if you want to, or talk to me during office hours. So now what? Right? We went from ore grade rock in the back of a haul truck coming out of an open pit mine. We've used a flotation cell to separate chalcopyrite from the gangue minerals. We dry that. Now we have a chalcopyrite separate on the right-hand side of the screen. What do we do next? Right? Chalcopyrite is copper iron sulfide. So the next step is to do what we call chemical beneficiation, and we have to break the bonds that hold copper and iron and sulfur together. So on the left-hand side of the screen is a photograph of chalcopyrite, and on the right-hand side of the screen is a schematic image of the individual atoms that make up the mineral chalcopyrite, where copper is shown in blue, iron is shown in orange, and sulfur is shown in yellow. And all I want you to take away here is that chalcopyrite as a mineral is held together by very strong bonds that connect copper to sulfur. Notice that each copper atom here is connected to 4 sulfur atoms, and each atom here of iron is connected to 4 sulfur atoms. Those bonds require energy to break. So now we want to separate copper from iron and sulfur, which means we're going to have to put energy into the system to break the bonds that hold copper and iron and sulfur together. Now, we've talked a little bit about this before. So earlier in the semester, we talked about how bronze is made, and I just want to have you think for a minute about how that process worked. How is bronze made, and what are the ingredients? So this is a slide I showed several lectures ago, and I talked about the ancient Sumerians who figured out how to extract metals from rocks by heating them to very high temperatures. And we term this process smelting. The most important part of smelting is this, the melting process. And I showed you a video, but here I'll just show you with still images, that what the ancient Sumerians figured out how to do is to take copper, which has a very high melting temperature, add a little bit of tin, which has a very low melting temperature, mix those up, so literally think of mixing them with a mortar and pestle, and then they would put them into a furnace, and then they would blow air with oxygen into that furnace, and by doing that, the copper plus tin mixture would melt at a lower temperature than pure copper melts, and they could pour that into molds, and that produced bronze. So just to give you a sense of the importance of mixing tin to copper, on the right-hand side is what we call a phase diagram. And all I need you to focus on is what I'll indicate here. The y-axis is temperature in degrees Celsius. And on the x-axis, we've got tin and we've got copper. On the right-hand side of the x-axis would be 100% pure copper. And on the left-hand side would be 100% pure tin or 0% copper. So as we go from left to right, we have an alloy or a mixture of 0% tin, 10% tin, 20% tin, 30% tin, and so forth across this x-axis. Ignore all of the words and fields here underneath the red line. All I want you to see is that tin on the y-axis, pure tin melts here, low temperature, and pure copper on the upper right melts up here at a very high temperature. And the red line shows you that as more tin is added to the tin-copper mixture, the melting temperature changes. So if we start with pure copper here that melts at a high temperature, as we add more tin, watch my laser pointer, the melting temperature of the mixture decreases. So if we have a mixture of approximately 50% tin, 50% copper, it has a melting temperature over here of about 650 degrees, which is give or take half of the melting temperature of pure copper. So the more tin you add, the lower the melting temperature. So back to chalcopyrite. We've got our atomic model here of chalcopyrite, copper in blue, iron in orange, and sulfur in yellow. And now we need to break the bonds that hold copper and iron and sulfur together. This is known as the science of pyrometallurgy. And for pyro, I want you to think about heat, fire, high temperature. And as I mentioned earlier, we also commonly refer to this as smelting. So we're not just melting chalcopyrite here, as the ancient Sumerians did. We want to melt the chalcopyrite, and after we melt the chalcopyrite, we want to separate copper from iron from sulfur. So how do we do that? We're going to do that by mixing the chalcopyrite with what we call fluxes. We're going to start with our chalcopyrite here on the left side. We're going to mix that with limestone, which has this composition, calcium carbonate. We're going to mix it with sand, which is quartz and has a composition of silicon dioxide. And when we mix these three solids together, so chalcopyrite plus beach sand plus calcium carbonate, which is what the limestone pyramids are made of in Egypt, we're going to put this into a furnace, and I'm going to show you first an animation of the process so you can visualize what's happening, and then I'm going to walk you through the details of the chemistry.
Blast furnace for the extraction of copper. A mixture of roasted ore, sand, and coke is dropped into the furnace and heated. Simultaneously, a hot blast of air is pumped in through the tuyers. Ferrous sulfide, the impurity, forms a fusible slag of ferrous silicate. The molten slag floats on copper sulfide that can be tapped off through the outlet. Matte, consisting of copper sulfide and traces of ferrous sulfide, sinks to the bottom and is tapped off through the lowermost outlet. Waste gases are let out through an outlet at the top.
So here's what I want you to see in the video, okay, and I'm going to walk you through the steps. What I want you to see is we've got what's called here a blast furnace. So think of it as a big vertical oven, furnace meaning high temperature. And in this video at the top, this roasted ore, think of that now as our chalcopyrite plus quartz plus calcium carbonate. We're going to pour that into the top of the blast furnace. Here is the source of heat, so we've got this very hot. We're going to push air into the blast furnace, and the air is important because oxygen will help generate higher temperatures. And what happens during the process is what initially starts out as a physical mixture of chalcopyrite and quartz and calcium carbonate, all three of those in the presence of high temperatures will melt. But when they melt, they don't melt to produce a single liquid. They melt and they produce two different liquids. And the analogy I want you to think about is making salad dressing. So on the left-hand side of the screen, we've got oil and we've got a really nice balsamic vinegar. And what happens if you take oil and mix it with balsamic vinegar and you shake it with all of your might? You will never get the balsamic vinegar and the oil to mix. They are not miscible. They are immiscible fluids, just like we talked about earlier with oil and water. So what happens in the blast furnace is that initial physical mixture of chalcopyrite, quartz, and calcium carbonate, it melts to produce two liquids. One of those liquids we call slag, which is coming out here out of this outlet. And the second liquid is called matte, coming out of that. And I just want to play it so you can see that that's what's happening during the video. That slag liquid is exiting here, and that matte liquid is exiting here. So that's visually what I want you to have in your mind as I walk through the next few slides. So we're going to blow our solid mix into the furnace and add oxygen. Okay? So here we've got a blast furnace here. It's rectangular. It's extremely hot. We're going to blow oxygen into that furnace here on the left-hand side. On the upper right-hand side is where we have our mix of copper ore, limestone or calcium carbonate, and sand or quartz, silicon dioxide. We're going to push that into the furnace here. And when that happens, all three of those solids will transition from solid to liquid. But what occurs is that the copper and sulfur in chalcopyrite will form one liquid, and that liquid we refer to as matte, and matte has a composition Cu2S, so two atoms of copper and one atom of sulfur. And that matte is what we tap coming out, in this case, on the left side of the furnace. And it's coming out of the bottom. So it's shown here at the bottom of the smelter in green. And it is coming out of the bottom because above it, this black layer here, that black layer is a second liquid that is composed of iron and silica and calcium. So we blow oxygen into the furnace. We heat it to about 1100 degrees Celsius. The oxygen in the air reacts with iron, and iron is in the chalcopyrite to form iron oxide. It leaves copper, so that copper reacts with sulfur to form initially a copper sulfide. Some of the sulfur is vented out of the top of the smelter as sulfur dioxide because some of the sulfur in chalcopyrite reacts with some of the oxygen in the air that we're pushing in to produce sulfur dioxide. The silicon dioxide from our beach sand up here, center top left, it reacts with limestone, which is calcium carbonate, and FeO, or the iron, to form a liquid that we call slag, which is composed of iron, silica, and oxygen, and calcium, silica, and oxygen. The density of slag is lower than the density of the copper sulfide liquid matte, so the slag floats, the matte sinks. We can put an outlet for the matte, and we can put an outlet on the right side for the slag, and we're literally tapping those, and we allow the two liquids to flow out of the base of the smelter. So now that we have our matte, which is Cu2S, the next step is to produce what we call blister copper, which is 98 to 99% pure copper. So we're getting close. Remember, we started with a rock that was 97% gangue, 3% chalcopyrite, which means that that rock had 1% copper. So we're getting closer. So the next step, as I highlight here on the right-hand side, is that molten copper matte is injected into a second type of furnace known as a converter furnace. That name you don't need to memorize. Where we again blow air through that matte, the air reacts with sulfur to produce sulfur dioxide, and that sulfur dioxide, not shown in the photograph, is vented historically to the atmosphere, but I'll talk about how we trap that today. And that allows almost pure, 98 to 99% copper, with a human for scale, 98 to 99% copper, known as blister copper, is literally poured out of the bottom of the furnace. So now we have almost completely eliminated all of the other elements that were present in that ore grade rock. And I've got this text on the bottom here, which we'll come back to and focus on in the next lecture. This also generates more waste, which we'll describe in detail. So this is a video, and I'll play it just to show you what that blister copper looks like coming out of the bottom of a converter furnace here. So that is blister copper liquid, 98 to 99% pure copper, and it's being poured into a mold. So this is a mold here that will not melt at those high temperatures. And that blister copper liquid is being poured out of the furnace, and then they'll move that mold to the right, lose a little bit of copper, but they pick that up. And so they just continually do this by feeding new material into the blast furnace and then into the converter furnace. So if we go back to thinking about copper 5,000 or 6,000 years ago, this is what we do today. The next step is what we call electrolytic refining, and I'm going to play the video first and then I'll walk through it.
Electrolytic refining is a process of obtaining pure metal. The electrolyte has to be the salt of the metal which needs to be purified or refined. Here we are trying to refine copper, so the electrolyte taken is acidified copper sulfate. The anode is taken as a thick rod made up of impure copper. Cathode is made up of pure copper and it is taken in the form of a thin rod. When current passes, copper sulfate, that is the electrolyte, dissociates into copper and sulfate ions. At anode, copper atoms
2 electrons to the anode and change into copper ions. These copper ions come into the electrolyte. The copper ions from the electrolyte get attracted towards the cathode. They gain 2 electrons from the cathode and in turn change into copper atoms. As more and more copper atoms get deposited on cathode, the cathode goes on becoming thicker. Atoms of copper are coming out of anode goes on becoming thinner. The anode, which was made up of impure copper, the impurities, they fall below the anode and get collected in the form of anode mud. Copper which is deposited on cathode is the pure copper and can be used for making electric wires or cables or utensils, etc.
Okay, so I apologize for that choppy audio, but let me walk you through what I want you to see. So we've now gone from blister copper, which is 98 to 99% pure copper. That in this animation is here on the left. That's going to be, let me just fast forward here to where we've annotated everything. Okay, so that's our anode over here, impure copper, 98 to 99% copper. Notice that it starts out with a larger diameter than the pure metal copper we've put over here as our cathode. There's electric current that flows between the anode and cathode, and this is a water-rich solution that contains, let's get to it, dissolved sulfate. And sulfate bonds with copper in the fluid so that copper sulfate is stable within the fluid, meaning that the fluid is saturated with copper sulfate. There can be no more free copper. So when the electric current is passed, copper from the anode will be lost to the fluid because the copper here, which is neutral, meaning it has an equal number of protons and neutrons, now it will have a deficit of electrons here. It will become part of the fluid and it will be drawn to the cathode, and the cathode will supply 2 electrons to copper. Thereby the copper goes back to a state where it has an equal number of electrons and protons, which means that it's a pure metal. And as a function of time, the cathode becomes larger and the anode becomes smaller. That's what I want you to see, that we've gone from blister copper, 98% copper, to cathode copper, or what is commonly referred to as cathode copper, which is 100% pure copper. So this is just a still image of that process, and that's what I want you to take away, that the blister copper anodes are immersed in an electrolyte that contains copper sulfate and sulfuric acid. The pure copper cathodes are arranged between the blister copper anodes. There's a current that's supplied. You don't need to memorize that. You also don't need to memorize these reactions. I just want you to have a holistic understanding of this process of converting blister copper or anode copper to pure copper, what we call cathode copper. And this is what it looks like on the left-hand side. So this gentleman here at the processing facility, he is standing on an iron metal grate, and below him is the electrolytic solution. Okay? An electrolyte, just think about Gatorade or Powerade, right? Electrolytes conduct electricity, so that's all we mean by an electrolytic solution. It's some sort of mine-grade Gatorade, for lack of a better term, although you'd never want to drink it. Would not make you stronger. And what's done here is that the copper anodes and cathodes are immersed into that electrolytic solution. Current is passed, and we produce all of these sheets of cathode copper, which is right now, if you're plugged into a socket on the wall, charging your laptop or your phone, there is cathode copper behind that wall connected to a supply of power at your local utility or solar panels or wind turbines somewhere that is allowing electricity to run into and power your device, just as it's doing for me in my lovely basement studio this Sunday afternoon. So it's quite a process, isn't it? We've gone from rock below the surface. We used magnetic X-ray vision to find it. We sampled sulfite, we sampled soils, we sampled stream sediments, we did our aerial surveys, we dug a massive hole in the ground, we used dynamite to detonate and disaggregate that rock, we put it into haul trucks, the haul trucks brought it out of the mine, we then physically beneficiated that rock by disaggregating it in a ball mill. We produced this flour consistency chalcopyrite separate. We used these we use the flotation cells here, top right, to separate chalcopyrite from the gangue minerals. We put it into a mixture of calcium carbonate and silicon dioxide. We heated it to 1100 degrees. We produced matte copper sulfide, Cu2S. We then put that through a converter furnace. We got rid of the sulfur by bubbling oxygen through that liquid. Then we put it through an electrolytic refining cell, and now we've got 100% copper that society uses. So I left out this exit number 4. That is where all of the gangue minerals go to a tailings pile, and we'll talk about that in the next lecture. I want to just leave you here with a few thoughts on the environmental impact and energy requirements. Just remember, we started with a rock that's 97% gangue minerals. Iron plus sulfur are another 2% of the rock. So 99% of the rock that the mining company is bringing up and out is waste rock. And remember, we've already also mined the overburden. So this is not the overburden. The overburden we got out of the way. We moved that into a big mountain of tailings. And now of every ton of ore grade rock that we're pulling out, 99% of that ore grade rock is waste material. And that is where environmental impacts become paramount. We need to understand the potential negative impacts on the environment from all parts of this process. So we go back to Bingham Canyon, and we'll talk about this in detail. The slag, the SO2, and all of that that's been produced since 1906 from this one particular open pit mine, one of hundreds on the surface of the earth. There's a lot that goes on behind the scenes, as I mentioned earlier, to increase the revenue stream from mining. And part of increasing the revenue stream is decreasing the costs of mining and beneficiation. So we talked about flotation. I just want to let you know, for those of you who are interested, there's lots of great stuff on the web that you can read about all of the energy inputs to the system, all of the energy that's lost, all the materials that are lost, and then this important part, the recovery. So the goal is to recover 100% of the chalcopyrite. Every 1, 2, 3, 8, 10, 15% of chalcopyrite that you do not recover is lost revenue. That should be an E instead of a T. So it's lost revenue that a mining company will not make. Just the last couple of slides here on energy. And both slides show you something different, and I want to make sure I emphasize and you understand the differences. So you can ignore the H and the P here, copper H, copper P, nickel H. P stands for pyrometallurgy. That's what I just talked about. That's the smelting. So smelting copper versus H, which is hydrometallurgy, which is a different type of beneficiation that I'm not going to discuss in this class, but feel free to join me during office hours and ask questions. So I've got here plotted a figure from our textbook. On the x-axis is what we call the solid waste burden, okay, which is in essence the energy required per kilogram of processing the ore grade rock and the overburden to make available to society copper or nickel or zinc or lead or aluminum or titanium or steel, which is dominantly iron. So think of this as iron. And on the y-axis is the global energy requirement in kilojoules per kilogram for each of these individual metals on a per kilogram basis. So the energy required for metal production per kilogram. So notice that titanium requires a lot of energy, but produces very little solid waste, meaning the energy required to produce titanium also requires very little energy relative to the waste burden. Steel also on a per kilogram basis requires very little energy and has a very low solid waste burden. Notice that lead and zinc are higher than steel Then we've got copper, we've got nickel. Nickel produced by hydrometallurgical processes requires a fairly substantial amount of energy and has a very high solid waste burden. So this would be aluminum. Remember we talked about bauxite? So this is now the energy per kilogram. Now the important thing is to think, okay, on a per kilogram basis, we can evaluate the energy required and the solid waste burden. But it's important to then scale it up to contextualize it in terms of the total quantity of each of these resources that we produce. And I'm going to focus your eye on steel. On this plot, where we're per kilogram, notice that steel is on the lower left axis here. Look what happens when we change things. So now the y-axis is global energy requirement in megajoules. And this means the aggregate total amount of energy required to produce all of the steel consumed by society every year. So this is on an annual basis. Notice that the total energy required for global steel production is greater than the global energy required to produce all of these other metals. So all of the aluminum in your cans of soda or bubbly or La Croix or beer, all of the copper that goes into our wiring systems, our laptops, our smartphones, all of the titanium, which is a metal that we use to make F-150s lighter so that they also, along with aluminum, can get better fuel economy. Titanium is also commonly used for golf clubs. Steel dominates, and that's because steel is the backbone for our built infrastructure. Every building, every road, on average, every sidewalk, every truck, every vehicle contains steel, and globally we produce so much steel that the energy requirement for it alone exceeds all others. This is a snapshot of the section of our book that describes this in detail, and so I'd encourage you to read that just to follow up on the words that I've used in the lecture today. And when we talk about energy, there's just a couple of things I'm going to highlight because this impacts the economics of mining. Energy constitutes a significant portion of the cost of steel production, from 20 to 40%. So for a mining company to produce steel, at the end of the mining process, when they go to sell that steel to a buyer, of 100% of their costs, 20 to 40% are energy alone. So anything that can be done to reduce the amount of energy required to produce steel, mining companies want that because that reduces their costs and increases their revenue and increases their profit margin. And you can see this in another way here, just to tie this to something you're going to be doing in discussion. This is the kilograms of carbon dioxide per million tons of copper concentrate. So going back to copper that is produced from ore-grade rock, this is the amount of carbon dioxide produced from all of the energy from fossil fuels when we drill and blast a mine, load it into trucks and haul it out of the mine, all of the ventilation on the surface for mining operations in an underground mine infrastructure. When we have underground mines and open pits, we have to dewater them because they often exist below the water table. Then we have crushing and grinding. So I mentioned mining companies now working with engineering firms to try and figure out ways to reduce the cost of pulverizing that rock. If you just look at the amount of CO2 per million tons of copper concentrate, this is an indication that this is the energy hog. This is the number one priority right now for mining companies, is to reduce the energy it takes to crush and grind the ore grade rock in order to separate sulfides from gangue minerals. And just, I think lastly here, global raw steel production consumes about 27 million gigawatt hours a year of electricity. DTE, as you now know, produces about 50,000 gigawatts of electricity a year. So hundreds more times electricity or energy is used to manufacture steel than we consume here in Southeast Michigan. And the images on the left, this is a steel structure that is the scaffolding on which we build all of our buildings around the world. So this is what I mean by steel is the backbone for our built environment. And then on the right-hand side, from the mining company's perspective, is good news. Between 1960 and 2017, the amount of energy consumption per ton of steel production has decreased by almost 60%. And if you decrease the amount of energy that you need to produce steel by 60%, you have just increased your profit margin by a similar amount of money. And that's it for this lecture.